Thank you guys for coming to our last presentation today. So this is group number 8, GreenerGrass. Very easy for me to pronounce. I've been butchering a lot of titles today. So Nick, Chris, and Corey.
Awesome. Anyone?
Good to start?
Yes.
All right. Afternoon, everyone. Afternoon, everyone, and thank you for coming to our final design presentation. We are GreenerGrass Undersoil Heating Solutions. I'm Nick Bachmann. I'm the Chief Safety Officer.
I'm Chris Blanchard. I'm the Chief Technical Officer.
And I'm Corey Chamberlain, Chief Financial Officer.
So before we begin, we'd just like to thank our Capstone advisor, Nick Mitra. Unable to join us here today, but he's been a great help. Doctors ChE and Webster, the great professors, and the entire Northeastern University chemical engineering community.
It's all right.
So again, the basic crux of our design project has been how we get an outdoor sports stadium in the middle of winter to go from this completely unplayable, snowed in, dangerous, and possibly causing snow delays, something that looks a little bit more like this. Playable, players are on the field, there's no delays, no safety concerns. So we do this using undersoil heating. Since about the 1950s, outdoor sports stadiums have started installing undersoil heating systems underneath the field and stadiums. The purpose of these systems would be to melt snow and ice and also promote grass growth. These systems started primarily as electric coil based. They evolved over the years to use fluid systems for heat transfer, but after that they have remained a kind of stagnant industry. Here's an example of the first stadium to introduce undersoil heating, Goodison Park, also known as the Grey Lady, home of Everton FC in Liverpool. So it's the first stadium in the world to install electric coils underneath the field in order to prevent snow buildup. This was replaced in the 1960s with a piping system, and it hasn't been touched really since that at all. So our design, we have designed a novel undersoil heating system designed to reduce energy expenses. And we do this by taking advantage of the thermal properties of a layered pipe material. This allows us to create a system using smaller pipes to maintain competitive manufacturing costs. And the main takeaway from this is that we have devised a method to decrease daily operation expense by the stadium by about 36%. So the current industry standard for undersoil heating, systems are expected to be run 24/7 throughout cold seasons, and they're constructed using cross-linked polyethylene piping. So that's a sort of a flexible hose-like tubing. It's chosen because it's got a low thermal expansion and a high operating temperature range. It makes it a fairly good material for running underneath a stadium. The pipes are laid in loops that span typically the length of a stadium, installed about 1 foot underneath the field with a soil and sand backfill. These systems can be up to 27 miles long of just piping, and they're run using water or ethylene glycol as a heat transfer fluid, heated with natural gas boilers in maintenance areas underneath the stadium. Here's an example of what one of these stadiums looks like when when the field has been dug up. Just PEX piping run across the length of the stadium. So we knew that early on that our technology would be best suited for stadiums. We decided this by taking a look at the market for undersoil heating. So we first considered using these systems for public infrastructure, parks, public gardens, even roads and sidewalks to prevent snow buildup. But these systems can be costly to run for just about anyone to constantly pipe hot water underneath an area. So these become difficult to justify for public projects. So we knew we wanted to go into the private sector. So we could consider the lawns and gardens of the wealthy. But right now, we consider this to be a limited market with less appeal than something that just about everyone could enjoy. That would be a difficult niche to break into. So sports stadiums is kind of the perfect niche for us. Stadiums are fairly expensive as is. They have the capital to fund installation and heating. They're already using it, as I mentioned before, with Goodison and other parks. And there's a genuine need here because adverse weather can disrupt leagues significantly, cause financial costs, and they create player safety concerns. And also an advantage to choosing a stadium designed for a specific sport is that usually the dimensions for those fields are standardized. So we can design one system that can fit into many stadiums. So after deciding on our market of sports stadiums, we had to decide a location. So we had to find a place where that has a cold climate that would actually require heating, where outdoor sports are popular and new stadiums are constantly being built or renovated to allow us to be constantly installing these systems. So we took a look at locally the United States, where football is fairly popular. The NFL had hit $12 billion in revenue in the 2014-2015 season, so they have an extremely high revenue that would absolutely allow for the cost of undersoil heating in stadiums to be viable. But the problem there is that the United States is has varied geography, and there's a finite number of NFL stadiums in the country, where only a small percentage of those would actually require heating such as this, located in the northern United States. A lot of these stadiums already have these systems like this installed. So we would mostly be focusing on renovation, which is not as easy an industry to break into. So we focused on soccer in Northern Europe. Soccer is the most popular sport in the world, especially in Europe. And it's an area where there's not just one league that dominates. Stadiums are constantly being built and renovated for new teams, and there are a lot of old stadiums that require updating. And the soccer season lasts from late summer through spring, which is ideal for our needs, where that hits right through the winter. So this is a difficult market to break into for a startup company. So we decided to operate as an R&D subsidiary of the Rehau Group, which is a polymer-focused materials conglomerate based in Switzerland, right in the middle of our target market. And they've had a very recent focus on pitch heating for soccer stadiums, which is our exact market. So Rehau Group has systems found in 170 stadiums worldwide, so that's a very large install base that we could begin with. Customers that already trust this company and might be interested in, for their next renovations, an improved version of their system. So the 170 stadiums include such landmark stadiums as the ones used for the 2006 World Cup in Germany and Euro 2012 in Poland and Ukraine. So we performed a strengths, weaknesses, opportunities, and threats analysis to assess the viability of our business venture. So we recognized a few of our weaknesses. We are a small R&D staff of 3 people, and it's a very cutthroat market, stadium building. But this is offset by our strengths, which we believe we have a very novel improvement on existing technology. Working with the Rehau Group, we have an established install base and a strong source of funding, as well as a prime market location in Northern Europe. We still need to watch out for threats such as competition, because this is an area that already has an established market that we're breaking into. We're not creating a new market. We always have to worry about the material price fluctuation of our consumable goods. And our market is dependent on the public's market for outdoor sports, which doesn't seem to be waning anytime soon, but it will fluctuate over time. These threats are offset by a number of business opportunities we have after we establish ourselves. We could perhaps leverage these systems in uses outside of stadiums or outside of soccer if we become successful in this venture. And working with the Rehab Group, we can also integrate our technology sideways with some of their other technology.
All right, so
Yeah.
I'll just so we know more about the market. We're going to start discussing more about our design, what makes our solution novel. So what we have is we actually have a directional design with a half shell of copper piping on the inside and surrounded fully by a PEX layer. And on the bottom half, we have a layer of insulation below that to further reduce the total heat loss through the bottom half of our pipes. So discussing this, we have, these pipes are very directional. Almost all the heat is being released through the upper half of the pipe towards the playing field, because that's what we care about as when we're heating the surface of the field, is what the playing field temperature is. And the insulation adds further protection from heat loss through the bottom of the pipe away from the field. And the reason we use PEX as a shell for this is because PEX has been proven to work within soil and is certified for burial and will not possibly erode to the soil contaminants through oxidation like copper will. Here's a cross-section of our piping. We chose to go with an inner diameter of 1.5 inches. And here we see that the copper is much larger than the PEX. For the shell, it's actually at a 3-to-1 ratio. That was specifically optimized for most economical versus how much heat transfer we wanted to bring to the field versus away from the field. Here's our key values that we calculated through optimization methods. Here we took heat loss from the surface of the field to the surface of the air, and compared that to the heat generated by our system, and then optimized for our specific pipe separation that we wanted, because we chose 12 inches as a safe pipe depth. So our pipe separation would be about 11 inches there. And when I say separation, I mean when the pipes loop back around to go across the field, the distance from one pipe to the next is 11 inches. The key thing to grab from this is that our fluid temperature is 42 degrees Celsius, and if we were to take a current system, just the standard PEX piping, it would be 64 degrees Celsius to heat the surface of the field to 10 degrees Celsius. So that's where our efficiency comes from, is just being able to keep the water at a much lower temperature compared to standard systems. Here's some of our assumptions that we made here. The first assumption that we made was that for all our calculations, we just left the temperature of the air at 0 degrees Celsius. Obviously, if the air was colder or warmer, it would either make our systems expend less energy or more energy to keep the field at 10 degrees Celsius. The reason we chose exactly 0 is because our biggest issue is frost forming on the field, as it imposes a big safety hazard to the players, because foot traction is very important when playing sports. And then to simplify a lot of our equations, we said that the lower half of our pipes radiate 0 heat. This was showed by the equations below, where we bring the calculation for the resistances of the total pipe and compare it to the total pipe as the insulation and the PEX resistances or conductivities go to 0, and that would and as we did that, the difference between the two was 1.1%. So we decided that that was good enough to say that the heat loss through the bottom of the pipe was negligible. To manufacture these pipes, we don't plan on actually having manufacturing in-house, and it would be either through another group within Rehau Group or through another company through partnership. The PEX material is going to be pre-mixed with the cross-linking agent in the polyethylene, and it's going to be through the silane method. Then the PEX will be extruded across the half shell of the copper piping, and steam will be flushed through that system to activate the agent and cross-link the polyethylene to make the PEX that we know. And then insulation, we suggest that the insulation should be adhered to the pipes during manufacturing, so we can know the directionality of the pipes very easily. Just pictures of the raw PEX and then extruder example. Here's our process flow diagram of a standard soccer stadium. And what we have here is the system has 980 total loops of piping, 490 per system. It's separated into 4 quadrants of the field, and each of those quadrants had 2 quadrants per boiler system. And there's a flow sensor every 10 loops, and I'll go further into this for the design. We would be using 16 total miles of piping. The focus is really on redundancy. As we look here, we have 2 boilers, 2 sets of pumps, and that is because we always want the system to be running 24/7 no matter what issues may arise. We don't want maintenance on one of the boilers to have to shut down half the field, so we have a valve system to allow for one of these boilers to operate for the entire field system. All of the components are rated to run for the entire field, and in standard operation they will be running at approximately half of their maximum capacity, but should any need come up for having to have one system run the entire field, that's possible. We have drain pumps in case the system doesn't need to run and we're expecting very freezing temperatures to occur, so we don't have freezing within our pipes. For installation, it's just a standard installation model for current undersoil heating systems, where you're going to be digging 12 inches underground, 12 to 15 inches underground, and we're going to be using sand followed by soil as a standard in most sports stadiums. And then it's a very good distance, 12 inches underground, because it's above the water table. It also allows for more sports to be played on the fields rather than just soccer. Like a field could be, once the pipes are under 12 inches, they could be rated for javelin throwing for like an Olympics event. A difference between our system and the PEX system is our system has copper inserts, and that makes it much more rigid than a standard PEX system. So unlike being able to unravel a giant hose of 16 miles, we have to have individual parts. But these parts will actually simplify fixing repairs, and can go into that later with instrumentation actually. So how it helps fix repairs, we have flow sensors every 10 loops, as I said, and so that actually gives us 998 flow sensors. So we can actually isolate where a possible leak in the system is to 1/98 of the total field, rather than having to dig up the entire field, find where the leak is, and then fix from there. We also have pressure sensors for safety on our boilers and our pumps, just to maintain that we are within safe operating parameters, make sure there isn't any backups. We also have thermocouples on our system to make sure that our system is actually keeping the surface at the temperature that we want it.
Thank you, Chris. So as everyone knows, the most important part is to make sure our systems are safe. We don't want our systems to have boilers exploding. That's very bad for press and for human life, obviously. So we have a lot of redundancy built into our system, as Chris mentioned. We have main and backup pumps, 2 boilers, 2 drain pumps. In any case of one system failing, the other system is more than capable of taking over and operating safely. So we ran an FMEA analysis, and we have, out of the entire analysis, we picked 4 key fail methods, and we talked about our way of mitigating those issues. We have valve faults and pipe roughing, which is isolated with the flow sensors, it was an additional cost, but we felt that the security of having those sensors was worth the cost. Drain pump operation is, thanks to the redundancy and the pressure sensors, we have good capabilities to take over in case something fails. Boiler pressure and gas flow. We have a system-wide shutdown emergency valve in case the boilers start to overpressurize or something to that effect. And calibration drift is made up for by the wide variety of sensors that we have. Even if 10% of our sensors fail, or are miscalibrated and getting faulty readings, we should be able to account for that, go and identify which ones are in error and fix them. Our system uses pure water as opposed to a water ethylene glycol mix that other systems use. We did sacrifice a little bit of thermal energy transfer, but we felt it was worth it in case we did have a leak. We didn't want to deal with any environmental concerns. We wanted to make sure it's just water in the field, which is, I hear, good for plants. I'm not too sure. And the system, the installation we are using is thermocell installation, which is rated for underground use. It is commercially viable. It is actually very inexpensive, as well as the PEX, which is rated for underground use. So we have our full analysis right here. Just a laser pointer. Yep, cool. So we'll just point out the few systems that we had. The system that we mentioned before had the highest RPN ratings. Just want to show you that even the worst issues that we could have still aren't going to be a major issue. Right here, a quick summary and cost breakdown of the equipment. We have our piping, all our systems, and our sensors, as well as the labor installation cost per system. The total comes about $716,000 per system. This includes the manufacturing, the shipping, all that. And we plan on selling these systems for about $1 million each, which is slightly higher than the market rate, but we feel with the price savings that we'll be giving the customer through energy, that we can justify that increased profit. To begin our system, we're going to have 3 years of research and development. The cost for those 3 years is going to be about $1 million. There's going to be the salary for 3 engineers to be working over the course of 3 years at $60,000 each, as well as $150,000 a year, mostly for computer modeling and materials for prototyping systems. We're going to be located in Coleman, Alabama, which is the Rayhus Group's North American manufacturing facility. They have research and development space there that is actually not in use. I called them last week. So they have space that's prime for us to move in. And we plan on, as I said, selling for $1 million, giving us a $300,000 profit per stadium. So ideally, we hope to sell 3 systems per year based on the current rate of stadiums being built through our market. That was a reasonable estimation. We don't think we'll get every system, but we'll get a decent amount. And it'll be profitable for us during the 5th year. So here's just a quick graph of our net cash flow. So as you can see, we have the 3 years of loss at $330,000 each. And then we have the income that we'll be making through our profits. As you can see, we'll be raising the price about 1% a year. Eurozone inflation is about at 0.8%. So this ties in and accounts for inflation. We have a return on investment of a 10-year investment. It's about 500%, a little more, 550%, which is, we feel, a very solid investment. It's worthwhile to the Rayhus Group to go after this, help increase their systems. Yes, and we just have a few other values. We have a nice plot showing that. And now this is really where our system shines, the operating cost comparison. So right now the current systems can operate at a range from $3,100 to $5,100 per day. A low-end system can cost downwards to $700,000 to install, while high-end systems such as the one at the Patriots Gillette Stadium cost anywhere from $900,000 to $1 million. Our system, we have managed to get the energy operating costs down to $1,500 per acre per day, which means that our daily operating cost for a soccer pitch would be $2,600. With an install cost of $1 million as the initial, $1,000, that'd be great. An install cost of $1 million to begin. We are, as I said, more expensive, but as you can see over here, the break-even range from a low-end to a high-end system can go anywhere from 120 days to a little more than 200 days of operation. So in a particularly cold winter, they can make their money back that they spent on our system in less than a year. And these systems are rated for about 10 to 15 years, so obviously we feel that our system is the most economically viable system. This is just a quick illustration of what I showed you before. This shows our three systems there, and the low-end system, as you can see, you may win on the initial investment when you're pushing into a stadium, but they'll be operating at much higher energy costs. Even the high-end system that they have, which are shown right over here, will still be able to get you the savings that you need quickly. So a very important thing, one of our final conclusions, is that because our system is much more more energy efficient, that we help insulate these stadiums. I didn't mean to put that pun. We help insulate these stadiums for fluctuations in the natural gas and the fossil fuel industry. Everyone knows that energy costs are going up. Fossil fuels are becoming more scarce. Natural gas is becoming harder and harder to find. This trend, even though it's been reversed slightly right now, in the long term is going to continue to increase. So an investment in our system now will pay off dividends in the long run. We pride our systems on being economically, not only economically but environmentally safe, much as reduce energy costs, helps stadiums reduce their greenhouse emissions. They can help market to like, we're the greenest stadium in Northern Europe, things like that. It's very good in a PR standpoint. And we feel that we are the most responsible system out there. Now just real quickly going to run through some ideas that we had for our system that we decided to discard. So we always knew we were going to put copper with our piping. We just didn't know how we were going to put it in. Initially we were thinking put copper flakes throughout the PEX. However, that would cause difficulty when the polyethylene is becoming cross-linked, which would sacrifice the integrity of the pipe. So we decided to go against that. The same thing happened with, we're going to have copper rods throughout the shells going straight through the pipes, but since PEX is flexible and we wouldn't be able to get them in perfectly, there would be some areas where we'd have gaps, and that could also lead to structural integrity. Another pipe layout that we decided to pass on is a cross-linked pipe reading system, which digs the pipes in much deeper and allows you to have more uniform heat flow. However, that increases the amount of pipes that you need. The length increases by quite a bit, which increases both energy cost and the initial investment. And now our system, we feel, has decent possibilities in the future. We can do research on different polymer systems for the pipes, so we can have a better alternative to PEX. The market possibilities, we think, have very good possibilities. Now that we've reduced the cost by this much, it's possible that we could start, as we mentioned previously, moving into different markets, move into the high-end clientele for personal systems. The average lawn is about 0.2 acres, which would cost about $150 a day to heat with using our system, which is, to me, quite a bit, but to some people out there, negligible compared to the landscaping costs in the spring. We use sideways integration to use our pipe to help run cooling systems instead, running in the opposite direction, having heat flow more easily into the water and pumping it out, as well as other applications of the radio group, as they are such a large multinational corporation. Thank you for your time, and we'll field any questions you have.
Questions?
I had some questions, but you answered them.
Cool.
But one other thing I was wondering, have you accounted for the fluctuations that are often seen in the price of copper?
So,
That's one place where your
Yeah,
cost to the customer could be.
We saw that could vary, but it's also, we weren't sure how we would count that in like a full market forecast. Also considering that our system uses a lot less natural gas than other systems, and that also has fluctuations in our benefit as well. So we weren't really sure exactly how to do that. So
Yeah, it's a hard one because you could be purchasing something for a job,
mm,
you know, all of your pipe, and I don't remember what your value was for your pipe estimation, but you know, and then 2 weeks later it could cost an additional 10 or 20%.
yeah, which would, we feel like it might eat into the initial profit that we'd make, but we could charge that back to the customer because our savings were that efficient
Right.
that even though as we try to avoid them paying that extra amount, if it's inevitable, they'll still end up saving money in the long run.
Absolutely.
I had a question about, I guess, the thermal conductivity through soil that is dry versus soil that is wet, right? Because you'll still have, if it snows, right, you'll still have a buildup of moisture
yes.
that would occur above your 12 feet of where your pipes are. Did you account for that, or is that even not necessary to account?
We actually did account for it. So we found a useful study that was actually done in late 1980s on different thermal conductivities for soils, be it astroturf, natural soil, and sand, both wet and dry. And we used I believe the value for the wet soil in our calculations.
Okay, good.
Mhm. I believe it was the U.S. Army Corps of Engineers, the Colt Research Labs in New Hampshire that did
Great.
that study. So
Yeah, as it turns out, finding K values for soil is more complicated.
Yeah.
No, that's great that you accounted for it.
You said these systems are set up to last 10 to 15 years?
So 10 to 15 is what we plan on supporting them throughout, but some of the systems that are existing today, still using copper pipes, have been in soil since 1970, 1980. I mean, the Denver Broncos had a copper heating system for 35 years, which they just actually replaced last year. So the systems do have longevity, and especially since we're using the PEX shell, the ones that are installed right now, since PEX has been signed to since the 90s, they're still being used today. So we do have longevity. We just, for the sake of the analysis, stuck to 10, 15 years.
Yeah, aside from regular maintenance due to occasional leaks, there's not a whole lot of degradation happening in our systems.
And you're definitely going after natural grass, not turf, or, because I have no idea what the trends are, you know, I know
Oh,
in
yeah.
the 80s it seemed like the trend was more towards turf, now
It's-
it seems like it's more towards natural.
Right now it is pushing towards natural. Actually, another football example, I know way too much about football. The Oakland Raiders had to change their field 3 times from turf to grass this season because of complaints. And with soccer pitches, they're doing a lot more running than football, so they need a softer surface. I used to be a runner. I know running on grass is so much better than running on turf.
Yeah, undersoil heating systems are still useful for turf because frost buildup still occurs,
Yeah.
but one of the advantages of a system like this is promotion of grass growth, which obviously will only happen with real grass.
Yeah. Yeah, and I know with the turf for soccer, there were all the complaints about the rubber that was being used, and you know, if it could get inside the players' lungs and create problems. That was during the Women's World Cup, I think, in Canada. There was players who were almost boycotting playing because of the use of rubber in the artificial
yeah.
field.
So a lot of soccer players also dislike turf because it has a different feel on the
Yeah.
ball, and they've been practicing 20 years to be the best at kicking a soccer ball on grass, not turf. So a lot of stadiums tend to go for grass.
Good. I love also, just as a side note, how you presented your, I don't want to call them failed design attempts, but your other, you know, a lot of people don't present that. And I
Yeah,
think
we
that
felt
was nice
we felt
to
it was
see.
more important to like also kind of at least have a look into what our thought process was that led us to this total design.
Very nice.
Mhm.
Great. Excellent. Well, thank you, guys.
Thank you very much for your time and questions.
And we're ready to play on the field with this
Totally.
piping.
Also, these are just a
Yeah,
quick
just-
summary of all the equations, all the terms we use in the
Terms.
equations, all the boring math stuff.
In case you asked about them.
Yeah, we had
So
them.
your K value is up there?
Mhm.
Is that, there it is,
Yes.
conduction coefficient of copper at least.
Yeah.
And PEX.
Insulation.
And insulation,
Yep.
yeah.
So funny story, we actually, the source I initially had for copper, it had copper and PEX on it, like for K values, and the K value for copper was completely wrong.
It was like, hold on a second. We
And-
got like halfway through and
Yeah.
it was
It
like,
happens, yeah.
Yeah.
And then, well, at least you realize.
we were doing the math and we're like,
This doesn't sound right.
It was absolutely terrifying, but
Yeah.
we fixed it,
Yeah, we
and
fixed it.
everything still works out.
And did you correct the source
Yeah.
that you
Yeah,
got it from?
we did not
Oh,
correct the
really?
source because I'm pretty sure the author is probably passed away at this point.
it was
It was a
Old enough study.
Yes.
Right.
All right, thank you guys.
Thank
you.
Really good.